So the last section of this course is on S2S applications. So these are specific examples of where subseasonal to seasonal forecasts are made and how those specific sectors are able to use those predictions. So let's start with subseasonal to seasonal prediction of weather extremes. Obviously this is useful for airlines, for shipping, for other transportations, energy companies, cyclones, tornadoes, and so on, which have extensive applications. And the example we start with this here is the negative NAO, North Atlantic Oscillation, which we will see in a minute, and the European blocking pattern, which both affect the direction of the storm tracks and how the lower Europe and the upper Scandinavian countries get affected by phases of the NAO or the strength of the NAO, and how the European blocking pattern, which lasts for definitely subseasonal timescales, has predictability. This is often also related to the jet stream and other pressure centers like over the Ukraine and so on and so forth. So here we are looking at the CRPSS score, the continuous ranked probability skill scores for various models. You can see here ECMWF, NCEP, CMA, COSER, JMA, and IFPW. Sorry. And you can see that these are the forecast range in days, and there is a level of CRPSS above which the information is usable. So the lead time here, obviously the main point is that we are not looking at weather. So in fact these have been smoothed with the 5-day running mean, 4 to 7 day running mean, sorry, because we are really talking about beyond the weather range, the S2S timescale. So obviously there is predictability in both, and almost all the models are able to capture it with some small differences. Obviously as the lead time progresses, the skill drops off and the score becomes negative, and that's not what is useful anyways. So what is North Atlantic Oscillation? It is related to the Arctic Oscillation that we talked about, and essentially the oscillation between the Icelandic low and the Azores high, when depending on the gradient here, the storm tracks are either veering more towards the north and bringing wet stormy weather to the region up here and making the lower Mediterranean region drier and warmer, and also creating warmer, drier weather over here, Greenland and North Canada, Labrador Sea, and so on. And on the western side over the US you have wetter weather, and when the pressure centers change in strength, you get often more zonal storms, which would make the Mediterranean region stormier and wetter, and the Scandinavian region up there drier and warmer than normal. Okay, so those have subseasonal time scale, as we saw NAO. We can look at the NAO index actually, which is the difference of this with some normalization, but it has daily so weather time scales as well as subseasonal time scales, which means it can persist in a phase for multiple weeks, and also has a lower frequency like interannual to decadal time scale. So that's where the predictability come from, plus the fact that it is able to affect weather patterns on both on a large scale across the Atlantic on subseasonal timescales. There are other low frequency variabilities or climate modes, you can say, which affect weather regimes. So they create so-called weather regimes. So here is the example of the polar jet stream, which is like a referee between the high pressure polar air masses and the warm subtropical mid-latitude air masses, and depending on the interaction between the cold polar air and or the strength of that versus the strength of the ridge warm air coming up, you can have these wobbles in the jet stream which create very strong weather. So it said jet stream puts down weather on the surface. So the jet stream is of course a westerly pipeline of winds, and when it wobbles like this, it is going over large ranges of Coriolis effect. Coriolis increases as you go towards the pole. So when you do this, you are creating cyclonic spin and anticyclonic spin, which by verticity conservation wants to pull it back. So if you bring cyclonic spin into lower latitude, the verticity is out of balance, then it wants to swing back, and if the anticyclonic spin goes up, then it wants to come back. So you end up creating these planetary scale waves, which are essentially Rossby waves. So you end up with these warm, unusual weather in one region of the high latitudes, while miserably cold Arctic air, snow, ice, sleet in another region, and so on. So for example, during Christmas you can have miserably cold winter or several days or weeks over the DC region where the politicians sit, and at the same time very warm no snow over Fairbanks, Alaska. So a politician can sit in DC and say, where is global warming? Why is it so cold? But they don't know that this pattern is creating these contrasting weather across the globe. So there are two vertices, the stable polar vortex here and the wavy polar vortex. That is the stratospheric polar vortex that we talked about in the context of ozone and so on. This is the strong jet stream here. So if it is stable, then this tends to be less wavy. If this becomes wavy, let's say internal variability, then that tends to push cold air down and create wavy patterns in the polar jet stream. So we have to be careful about which vortex we mean. People often think it's the polar vortex by the polar jet stream, but actually that's a permanent feature there throughout the year, gets stronger during the winter because that depends on the equator to pole temperature gradient and so on, whereas this is up in the stratosphere, is very much a winter time process that tends to have its own variability. But nonetheless, those create weather regimes on the surface which have predictability. Another example is of course the El Nino. So we are looking here at El Nino during December, January, February, and La Nina during December, January, February, and El Nino during June, July, August, and I placed this in the wrong place, but anyway, here is a nice animation from AGU. AGU EOS journal had this animation of the polar vortex, and then it shows a slice through the stratosphere and the troposphere. Okay, so just to conclude this thought, sorry, this somehow the computer is jumping around. El Nino typically tends to produce anomalies in terms of temperature and rainfall. Remember, we said the El Nino has an impact on Indian monsoon, but Indian monsoon happens in June, July, August, whereas El Nino peaks in December, January, February. So a strong El Nino can have an impact on the monsoon while it's growing 6 months before its peak. And El Nino also creates weather regimes. For example, Indian monsoon is made up of active and break periods. Those length of the active break periods and the number of active break periods within the strength and the numbers within a year changes based on El Nino or La Nina, for example. Okay, so you can see that El Nino and La Nina are not necessarily symmetric. There is a slight asymmetry in that. Even in the strength of the El Nino and La Nina and so on, and there are reasons why those happen. You can go and listen to my El Nino podcast if you wish. Okay, so again, using the fact that El Nino is predictable, it's a low frequency variability, it has predictability, and it produces weather regimes like MJO impact, MESO impact, and so on, then we can use that for making some S2S timescale predictions of heat waves, extreme rains, droughts, cyclones, and so on. So we will see later on that actually the impact of El Nino extends to cyclones and presumably even to tornadoes and so on. So obviously this is a multi-scale system where low frequency variability is affected by high frequency variability, as we talked about before. Synoptic scale influencing the S2S time scale, and S2S time scale influencing the seasonal to interannual time scales. Okay.